Hey everybody, welcome back to Data Mining and Predictive Analytics. I am Dr. Nick Bolton, and today we're going to be talking to you about clustering in general, and more specifically the K-means clustering algorithm, which is a great, easy algorithm to implement for grouping like records or observations together based on a certain amount of criteria. So we're going to jump right into that. So, in general, defining what is clustering. Clustering is a collection of records that have some type of similarity. All right. These are referring to groupings of different records, observation cases, and grouping them into cases of similar objects. So, when we have a whole bunch of data that has no rhyme or reason to it, can we grab these different similarities and group them based on certain characteristics? All right. Clustering is a type of unsupervised learning model. Okay. And remember when we talked about differences between supervised and unsupervised? With unsupervised learning models, we don't need to have an outcome. We don't need to know the classification of each of these observations or records. So it can strictly just be unlabeled data. Just throw it into the algorithm and let it figure out what the similarities are. And we'll talk about how it does that here in a second. So there are a couple different clustering techniques out there. These are just a list of the few ones. We're going to specifically look at K-means clustering, but hierarchical clustering is another algorithm that groups different records based on similarities, as well as the Cohen networks. Some of the other, and the textbook talks a little bit more about each of these, I believe, in chapters 19 and 20, I believe. So if you're interested in learning more about those, please jump into that. Some other honorable mentions: the fuzzy means and the Gaussian mixture models, GMMs, as well as the Birch clustering techniques are all described a little bit more in our textbook, but we're going to really just dive into the K-means clustering. Between the two, there are two types of clusterings. Partitioning clustering, which is what we're talking about when we talk about the K-means clustering. This is dividing the data up into non-overlapping subsets or clusters, so that each of those clusters does not intersect with another. All right, so they're completely distinct in some type of way. Hierarchical clustering is a set of nested clusters that can have some overlap, all right, and is usually displayed in a kind of tree type. The partitioning clustering, here we have just some random data that is taken out, and we create as many partitions as we want to from the data, all right, and so we usually tell how many partitions we want to give the algorithm. So if we want to partition it into 20 clusters, we can do that. If we want to partition it into 2 clusters, we can do that. Some of the examples of different partitioning clustering that we see in healthcare: identifying high-risk groups. So K-means is really good at grouping patients based on different factors such as BMI, age, blood sugar levels, things like that, to identify individuals who are at high risk for certain diseases or disorders such as like diabetes, cardiovascular disease, and things like that. Tailoring specific treatment plans for those people. So by understanding these different factors, all right, within a patient cluster, healthcare providers can provide more personalized treatment plans and resources that they allocate to these patients. All right. Another example: predicting diseases or disease progression. So by analyzing different patient data, K-means can really identify clusters of patients with similar disease progressions, all right, or patterns that allow for better interventions and better outcomes of these patients. Hierarchical clustering is another example, or the different type of hierarchical clustering that we see in. So there can be some similarities between individual records, but it shows you the pattern of trying to identify what groups of these individual records having similarities, right? And so some of the examples of this is like breast cancer analysis. So hierarchical clustering can help identify different subgroups within breast cancer patients with distinct characteristics and therefore have different or similar prognosis. All right. Tuberculosis treatment, identifying clinical pathways and predicting treatment outcomes in tuberculosis patients. And then also, most commonly, I see hierarchical clustering used in gene expression, where clustering lots of genes may exhibit similar behavior. All right. And so, if you're looking to do gene modification, turn certain things off, turn certain things on, you can really identify what genes have very similar behavior. So the one thing to know about, especially partitioning clustering, is that clustering can be ambiguous. All right, so if we look at this raw data that we have here, some random data points, and you were to look at this and say, well, how many clusters do I want to partition this into? Okay. Well, if I'm just looking at this data and eyeballing it, you would think, well, maybe we can partition this into 2 clusters. All right, that seems easy enough. There seems to be 2 relatively distinct clusters. But if you look, squint hard enough, maybe there's many 4 clusters in here. All right, that you might want to partition this data set into. And if you look at this even more closely, you might even think you could partition this into as many as 6 clusters. All right, and so really this is subjective to understanding how to separate the data into a certain amount of clusters. And so is there a better way? Can we come up with a better way of being able to partition these into distinctive clusters? And I'll show you guys that in a minute. So in k-means clustering, each cluster is associated with a particular centroid. All right, and that's another term you should be familiar with when we talk about k-means clustering. And a centroid is nothing more than a center point. All right, and the center point is usually a mean of the data points that are surrounding it in some kind of way. And so each point within that cluster is assigned to a centroid. All right, and so each point in there is assigned to that centroid, which is going to be the closest data point to it. Right. We must specify the number of k. All right, the number of clusters before we begin our iteration. All right. And so just like in when we talked about the k nearest neighbors algorithm, all right, this is very similar where we have to assign a value for k to understand how many clusters we want to create. All right. With k-means clustering, initial centroids are oftentimes chosen randomly. All right, and so where those centroids get placed, all right, in the initial training of them is oftentimes randomized. All right, and so each iteration may vary from one run to another. I'll have a visual here in a second that illustrates that. The centroid is typically a mean of the points of the cluster. We talked about that. And the closeness of each of those data points within each cluster is measured by Euclidean distance. And we'll talk about that. K-means will converge for common similarity measurements based on those Euclidean distances. And I've got some math descriptions on that. All right. So again, with k-means clustering, obviously you have to choose the k, the number of clusters that you want to separate your data into. All right, and so there are optimal ways of creating clusters and there are suboptimal ways of creating clusters. So we want to pick k very carefully. All right, so if I have original data points here and I go, all right, there are obviously 3 clusters, but if I separate this into 4 k's, right, or 4 clusters, then I'm going to get a suboptimal clustering where I've got this grouping here, which obviously should all be 1 grouping, all right, not necessarily 2. All right, so it's very important to choose those initial centroids and where they're going to be located. So initial centroids are chosen randomly, and so therefore the clusters vary from one run to the next. And so what happens is that when you say, in this instance, I want to choose 3 groupings, I want to have 3 groups, I want to have 3 clusters. All right, initially those 3 clusters are going to be selected randomly based on the data set. All right, and so in iteration 1, we can see the 3 centroids are placed in this vicinity. All right, and as more data points come online in each iteration, all right, the actual centroids are going to start to migrate out to their specific locations. All right, and so it should get better and better by each iteration. So when you run k-means, it usually iterates many times until it reaches a convergence. All right, and that convergence being the algorithm we're going to talk about. All right, and when we minimize the distances of each of the centroids and maximize the distance between each of the centroids. All right, and so these repeats continue for each new record that is added on over and over and over again. All right. So how do we get this optimal, all right, separation of our clusters? So if we were looking to create an optimal clustering, all right, how do we optimize this? All right, well, we do that using the within sum squares approach. And so the criteria for us adding a new record, all right, to a group is based on the Euclidean distance. Remember, we talked about that last time. The distance between, the actual physical distance between the 2 points. All right. So if we have indexes of each of those observations, and we'll denote those as being C1 through however many observations we have, then those observations must satisfy 2 properties. All right. Here's 1 and here's 2. I'm not going to jump into these a whole lot, but for the first property, each observation belongs to at least just one K cluster. All right, it has to belong to one cluster, each observation, each record, right? And then 2, the clusters are non-overlapping, or an observation cannot belong to either or to more than one particular cluster. So you can't have one record that exists in 2 different clusters. All right, it can only belong in one. All right, and so this continues for each iteration, all right, and the algorithm will end up terminating when the centroids no longer change, all right, they're no longer moving around, or when a convergent criteria is met, all right. And so the goal, all right, when using the within sum squares approach, all right, is to minimize the intra-cluster, all right. So if I have a cluster, we want to minimize the intra-cluster, which is the distances between each of the points within the cluster, all right, and maximize the inter-cluster, all right. And the inter-cluster is the distance, all right, between each of those clusters individually, all right. And so I want to maximize that distance. So if and mathematically this is described as this, all right. So if the within clusters variation for K, for CK, then we call that a function, all right, W of C sub K, all right. And so this is the amount that each observation within a cluster differs from each other, all right. And so therefore we want to minimize, all right, how much each of those observations are differing from one another, all right, within the cluster. In other words, we want to partition the observations in each cluster such that the total within some variation summed over all K clusters is as small as possible, all right? That's the minimizing the within sum squares approach, all right? All right, there's a lot of different ways to define this concept, but the most common way is looking at the squared Euclidean distance. All right, this is the equation for the squared Euclidean distance. In other words, the within sum square, or the within sum variation for each cluster is the sum of all the pairwise squared Euclidean distances between the observations, all right, divided by the total number of observations in the cluster. And this is what we call K-means clustering. So when I talk about the K-means clustering, this is the algorithm. All right, this is the algorithm that utilizes the minimization of the within sum squares approach to minimize the intercluster distances and maximize the intercluster distances. I know that's a mouthful, all right, but that's the algorithm, all right. In application, it's a lot easier, all right. So it's a lot easier to apply this using a statistical programming language than to actually go in and calculate each one of these for each observation, okay. And the way that we do this, all right, is using these scree plots, all right. I talked a little bit about this last time, but basically what we're going to do is plot, all right, what is our within sum squares calculation for each number of clusters, all right. So here's k equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all right. And what we'll see is that we're trying to minimize the within sum squares, so we want this to go down, all right. But we also want to look at, we want to reduce our bias, all right. So we want to look at where the actual elbows are for this, all right. And so there are a couple elbows that we see within this data point. For this particular elbow, as it rises and falls, I would take n equals 5, go back 1. That's usually the way that you do this. Go back 1. I'd probably choose either 4 or 5 clusters for this particular, not even knowing what the data set is, just looking at the scree plot. And you can run a scree plot a couple of times over, all right, to try to reduce some bias or get a better looking elbow. Sometimes that helps you out for determining the number of clusters. But this is when we're trying to apply our k-means approach and understand or figure out how many clusters we want to have, how many k's we want to have. This is one of the best ways to do this, looking at the scree plot, determining where the elbow is and finding out where the number of clusters are for that. And so now I'll have 4 centroids that will iterate over many iterations of the algorithm and determine where those centroids should be located. All right, and then finally, just to wrap everything up, these are some of the positive and negative reasons to use k-means as a machine learning model. All right, one, it's easily implemented. All right, you don't need to know anything about your data. You can simply assign new data sets to existing clusters. All right, so if I have an existing k-means model, all right, and I get a new set of data, throw it in there, all right, and it's going to at least categorize that data, that observation, into one of the clusters. All right, and so this is very easy to implement. It's very easy to describe and talk to people who don't know anything about machine learning. They usually understand, all right, I have clusters of things, and you know, this cluster has, you know, these particular attributes. This one has these particular attributes. So it's very easy to talk about. All right. Some of the downsides of k-means is it doesn't handle categorical variables very well. So obviously we're using Euclidean distance and minimizing, you know, an optimization function basically, all right, for this particular model. So if we try to give it categorical data, it's just not going to know how to handle that kind of stuff. All right. Another bad thing is those initial centroids, all right, are very sensitive to that initialization. So because it's randomized, all right, to start with, sometimes one, it may take a long time to actually to stop, all right, or to come to a conclusion, all right. You know, and that may end up in a local minimum or something like that. So you have to be very careful when doing this and being aware that that's an issue. All right. Variables also should be measured on a similar scale. So we talked about this last time. Min-max normalization, making sure that variables that have very large ranges are not over impacting your model. All right. All right, and then you could always guess the wrong number of clusters. All right, that could be, I mean, because you are deciding how many clusters to have, you could always end up, I mean, as easy as it is to try to do this, you can do it poorly. All right, and so understanding or following the ways, looking at scree plots, running it a couple of times, trying to figure out what is the best K to use. Sometimes it's just you may choose the wrong one and end up with a poor performance of your model. All right, so that's about all I got. All I got for you guys today. That's what I need for you guys to know about K-means. And we'll leave it there today. If you got anything, feel free to email me. Have a great day, and I'll talk to you later.